In part 2 of this unit on electric potential, we focus on how to calculate the electric potential difference for various charge distributions. We're going to consider 3 general cases. Okay, the first being how to calculate the electric potential difference given that we know the form of the electric field, okay, surrounding the charge distribution. Secondly, we'll take a look at how to calculate the electric potential difference for a discrete charge distribution. That is a charge distribution consisting of a finite collection of point charges. And thirdly and finally, we'll consider the more general case of how to calculate the electric potential difference for a continuous charge distribution. So, as stated, let's start with this first general case. That is, given the form of the electric field, okay, surrounding a charge distribution, given that that is known, how can we calculate the electric potential difference from that? Well, let's start with our definition of electric potential difference. Okay, here we have our uniform field. I'm showing you pictured on the right-hand side of your screen, and we're asked to calculate, okay, the potential difference between 2 arbitrary points in that field region. Here's our initial point A and our final point B. All right, so I'm showing you one of many paths that could be taken between A and B, and I will show you that infinitesimal displacement vector ds, okay, a small, okay, piece of that path. Now, to calculate the electric potential difference given the field, we're just going to use our definition of electric potential difference, right? We have it expressed as this line integral, where our integrand here is, okay, this dot product of the electric field with the displacement vector ds, okay, for each infinitesimal segment of that path. Now, you'll notice here that because the electric field is constant, okay, anytime you have a constant within that integral, it can be taken outside of the integral. So we're free to express our integral as follows, okay, in which case, okay, the electric field and the dot, okay, operation are taken outside of there. So what we're left with in the integral is simply summing up all of these displacement vectors. And when you do that, okay, when you sum up all of your infinitesimal displacement vectors to get the total displacement, okay, I'll show you that in a second here, okay, you end up with, okay, a displacement, okay, delta S, which I'm going to show you right here. So note here that the potential difference depends only on the points A and B and not on the path taken. Okay, applying the definition of electric potential difference to any path would yield the same result. But remember, when you talk about the displacement, okay, you were talking about the change in position between points A and B. And what I'm showing you here with the vector delta S, okay, that represents the total displacement, okay, between those 2 points in space. So this is a fairly common, like I said, yet important, okay, result. How to calculate that potential difference given a uniform electric field. All right, so let's apply this to a particular example. And in this example here, okay, of the television, it says that while Bongo is watching the farm report on television, okay, an electron at the back end of the TV picture tube is accelerated towards the front end of the tube in a uniform electric field of magnitude 600 kilonewtons per coulomb, okay, that extends over a distance of 5 centimeters. So here I'm showing you the CRT. All televisions used to, okay, and all computer screens used to be cathode ray tubes. Okay, so this is maybe old school technology here. And that electron, which is thermally excited at the cathode by heating it up a little bit, can get enough kinetic energy to actually leave the cathode. It is then accelerated in a uniform field region provided by a parallel plate capacitor. Now, the first thing we're asked to do in this problem is to find the potential difference between the back and the front end of this field region. So where you see the green over here on your screen, okay, that would be where your television screen would be. Okay, that would be the front. So notice here that since the electron moves, okay, from the back to the front, okay, then the electric field must point backwards, right? Electrons are negatively charged, and we know that they naturally move opposite the direction of the electric field. As positive charges that move in the direction of the electric field, okay, by definition. So we have the direction of the field, which is shown to you here, and we're going to use the definition that we derived on the previous slide. So the change in electric potential from back to front, that is the electric potential difference, okay, from back to front, is given by, okay, the opposite of this dot product, the electric field dotted into the displacement. Now, you'll notice here that, okay, the electron moves opposite the field. So when we take that dot product, we're taking the cosine of 180 degrees. So we have the negative sign, okay. We're told that the electric field, we know its magnitude is 600 kilonewtons per coulomb. We know the electron moves a distance of 5 centimeters, okay, in traveling. And when we do the number crunching here, notice the negative sign and the cosine 180, those negatives will cancel out. We come up with an electric potential difference of 30 kilovolts, 30,000 volts. So as you can see, you know, televisions can be dangerous. In this case, because there's a high voltage, and we'll see the difference between having a 30,000 volt charged dome of a Van de Graaff generator and a 30,000 volt electric potential difference provided by an electrodynamic situation, okay, like what you could have in the CRT, and we'll have to wait to see the difference when we get to the study of electrodynamics. So, secondly, we're asked to calculate the change in potential energy of the electron, okay, as it moves from back to front. Well, remember that the electric potential difference is defined in terms of, okay, the change in electric potential energy. So you need to be able to go from one to the other. So this is just our definition, right? So the change in electric potential energy is just equal to the charge of the electron times the change, okay, in electric potential, okay, so, or electric potential difference. Here, remember, okay, Q, charge can be positive or negative. In this case, the electron is a negative charge carrier. We know the potential difference of 30 kilovolts. Okay, we convert that to volts. We come up with a change in electric potential energy of 4.8 times 10 to the minus 15 joules. So you can see why the electron volt is a much more user-friendly unit, okay, for when you're talking about individual charges. Notice here that, okay, the sign is negative, okay, and that negative sign tells you that, okay, the electron is losing potential energy, okay, as it is gaining kinetic energy, as its speed is increasing. And finally here, we want to calculate the electron speed as a result of this acceleration, assuming that it starts roughly at rest. Okay, so just the law of conservation of energy here tells us that, okay, if energy is conserved, if mechanical energy is conserved here, then the total change in potential energy plus whatever change in kinetic energy it experiences must be zero. Okay, if there is no total change in energy for this system, for this electron, in which case we can say that the change in the electric potential energy is just equal and opposite to the change in kinetic energy. And we know the change in the electric potential energy. We found that in part B of the problem. Okay, let's set that equal to change in kinetic energy. Starting from rest, the change in kinetic energy is just the final kinetic energy, 1/2 mv squared. We plug in the mass of the electron here, okay, the 9.11 times 10 to the minus 31 kilograms. And when we solve for speed, we come up with a value of about 1 times 10 to the 8th meters per second. Notice that the speed of light is 3 times 10 to the 8th meters per second. This is really incredible. This is amazing. Think about what this implies, that in a distance of about 5 centimeters, you can take an electron, which starts off at rest, and you can accelerate it in a 5 centimeter distance to about 1/3 of the speed of light. Okay, pretty incredible. So what is the electronic device that is capable of producing uniform or constant electric fields? Well, it turns out that it is an electronic device called a parallel plate capacitor. And we're going to talk in great detail about this circuit component in the next unit. Okay, they're that important. Okay, but for now, let's just consider a parallel plate capacitor to be two equal and oppositely charged conducting plates that are parallel to each other, that are separated by a distance, let's say d. And if we ignore the small fringing at the edges of the plates, okay, then we can consider them to be creators of uniform electric fields. And so it's important to know, what is the electric potential difference, okay, for a parallel plate capacitor. Well, here's our definition of electric potential difference. And we would say that the potential difference can be positive or negative, okay, depending on whether we're talking about going from the negative plate to the positive plate, or vice versa, from the positive plate to the negative plate. So here we'll say that when you're moving in the same direction as the electric field, okay, that is if your starting point is a positive plate, okay, and your ending point is the negative plate, then we would say that the electric potential difference, okay, is given by, okay, well, when you use your definition here, magnitude of V, which we'll say is E, times magnitude of the displacement, which is just D, the distance between them, okay, times, in this case, the cosine of 0, since the field and the displacement are in the same direction. So the negative sign tells us that the potential difference is negative, which would mean that if a positive charge was to move, okay, in the direction of the electric field, it would experience a loss of, okay, electric potential energy. Okay, likewise, when you move in the reverse direction, okay, here when you're moving from the negative plate to the positive plate against the field, okay, and you go through the process here, you use the definition. Now we're talking about, okay, the magnitude of the field times the magnitude of the displacement, which is d, in this case times the cosine of 180 degrees, okay, since the field and the displacement are in the opposite directions, in which case the negative signs will cancel, and in that case, okay, your electric potential difference is positive. Okay, and remember on, okay, our first video on this topic, okay, we said that when you move closer to a positive charge distribution, okay, to a positive source charge distribution, okay, in that case, the electric potential increases. And that is what we're showing here, okay, when you're moving in a direction opposite of the electric field. So you're moving closer to the positively charged plate. So in this example problem, we will once again look at how to calculate, okay, the electric potential difference, okay, for a charge distribution where the form of the electric field is known. And you may recall when we applied Gauss's law, we know what the electric field looks like for a cylindrical charge distribution, okay, as is the case with a power line. And we'll find out here in this problem, this is a rather important and practical application that you would find in, okay, long distance power transmission, like from the source of the power, the generator, to a substation, okay, much nearer a population center of the city. So here we're told that a long straight power line is made from wire of radius 1 centimeter, carries a line charge density of 3 microcoulombs per meter. Assume that no other charges are present. Okay, what is the potential difference between the surface of the wire and the ground, which is a distance 20 meters below the wire? So let's start by reviewing the form of the electric field. Okay, and you look at this result. You derived this previously using Gauss's law for electricity. Okay, and we showed that there is this inverse dependence, okay, between field and distance r, and that, of course, the strength of the field is directly proportional to the linear charge density, the line charge density, inversely proportional to the distance that the field point is from the line. And due to the high symmetry, okay, the electric field is in the radial direction. So I'm showing you in the diagram on the right-hand portion of your screen, the blue electric field vectors, okay, point radially away from the source, okay, from the wire itself. And here, okay, once again, r hat, remember, is that unit vector, and as always, it's directed from the source charge to the field point. Okay, in this problem, because of the symmetry, it is pointing in the radial direction. So given this, let's simplify the integrand. Okay, remember the electric potential is minus the integral of E dot ds. Let's just start here by taking a look at this integrand here, E dot ds. And we see here that, okay, we know the form of the field. Okay, ds, that infinitesimal displacement vector from your beginning point, okay, at the wire to your ending point on the ground, okay, that infinitesimal displacement vector, here the shortest path is in the radial direction. So for this particular problem, we can write that infinitesimal displacement vector as simply r hat times dr. And this allows us to greatly simplify things. When we plug in the expression for the electric field as well as the expression for ds, okay, we find that, okay, we end up with, okay, you know, r hat dot r hat, which is just 1, okay, times dr. So the form of this integrand is quite simple. Okay, this is what it is. We're now ready to integrate here to find the electric potential difference here, okay, between wire and ground. And here, when we do so, we can take out all of the constants, the lambda and the 2 pi epsilon naught. So what we're left with in the integral is simply, okay, the integral of dr over r, okay, which you know very well, okay, is simply the natural logarithm of r when you evaluate the integral. And we need to evaluate it from, you know, our starting point, which is at the surface of the wire, okay, to our ending point, which is the ground. So notice in the picture here that r sub a, if we're saying the center of the wire is the origin of the coordinate system here, okay, of this coordinate r, then, okay, r sub a, where is given to us in the problem here, is 1 centimeter, okay, or 0.01 meters. Okay, r sub b, the ground, which is 20 meters below, okay, we could write, you know, okay, we're okay, assuming here that it's 20 meters below the center of the wire, okay, in which case, when we plug in our numbers here, okay, let's do that here, and you will see that, okay, given the surface, the linear charge density here, okay, and making sure that we use a consistent set of units here, the SI units, we find out that the potential difference is negative 410 kilovolts. And look, this value is typical of long distance electric power transmission lines, okay, like you would find running from, okay, the generator, okay, where the source of the power is, okay, to a substation near the population of the center of the city. So, you know, you're not going to find these kind of voltages in town, but for example, you know, MID running along the the canal banks, okay, those high voltage lines can be on the order of several 100,000 volts. When we take a look at the sign here, why negative? Well, remember, because charge on the line is positive, which means that moving away from the line in the direction of the electric field means that you're moving from a high electric potential to a low electric potential, okay, in which case the potential of the ground is lower than the potential of the wire. So your potential difference, the change in potential, is going to be negative. Remember, the change in electric potential difference, okay, it goes like electric potential energy here. So here we have the answer. I just want to point out here that okay, the electric potential of a charged spherical conductor can be found using the same process here that we use. Since we know what the electric field looks like for a sphere, we know about the radial symmetry. Okay, we can use you know, a similar unit vector r hat here. And like I said, given that we know the electric field, okay, this displacement vector here, and I should say we know the electric field both inside and outside of a charged conductor, okay, we could then integrate, use and figure out the electric potential difference from our knowledge of the electric field for a spherical conductor. I'm choosing not to do it here, okay, it is in your textbook, you can read about it in your text, okay, very similar to the problem that we did here, however. Thus far today, we've seen that given the form of the electric field, okay, surrounding a source charge distribution, we can use the definition of electric potential difference to calculate the electric potential difference between 2 points in space surrounding that charge distribution, so long as the form of that electric field is known. Okay, so that's the first way to calculate an electric potential difference. Okay, a more elegant way, if you have a discrete charge distribution, okay, is what we're going to talk about now. Now, a discrete charge distribution is simply a collection of point charges. So if we know how to calculate the electric potential difference for a single point charge, okay, then we should be able to calculate the electric potential difference for a collection of point charges. So we're talking about, okay, in this problem here, let's start out by calculating the electric potential difference between 2 points in space, okay, due to a point charge Q. Now this point charge here, that is our source charge. Okay, this is a source charge distribution. We've got 2 points in space A and B, and in order to use our definition of electric potential difference, we need to move some field charge between those 2 points in space, calculate the change in electric potential energy for that field charge, okay, and then divide through by the field charge. That's the definition of electric potential difference. So this first point here, first point A here, we're going to assume is a distance r sub A from our source charge Q. And the second field point here, B, is a distance r sub B from our source charge Q. And we're going to look at some arbitrary path here, okay, connecting these 2 points. And I'm going to say here that we know what the electric field looks like at all points in space for a point charge. Okay, this we've done previously, and here's an expression for it. Okay, remember that unit vector r hat is directed from the source charge to the field point, okay, where the field charge is located. So here I'm showing you one of these field points along our path here, okay, from A to B. And once I show you that, we would say that this unit vector r hat would be directed as follows. Okay, and this value r here is the distance between the source charge and the field point and the field charge that exists there, okay, while we're moving it. So here, notice that the direction of the electric field, I'm going to show you at that field point, right, it is radially outwards, okay, and I will show you the displacement vector at this point here that, okay, is, I drew it rather big, but it is showing you the direction of the path at that field point here. All right, so simplifying the integrand, okay, to electric potential difference is, remember, minus, okay, the integral of E dot ds. So let's start by finding this integrand. Now here, I'm kind of showing you with this blue circle here, okay, we see the vector E, we see the displacement vector ds, and notice here that, okay, we have our expression for E here, okay, which, okay, has a magnitude kq over r squared, okay, direction given by r hat. So we need to take a look at this, okay, the dot product of this vector r hat and ds. Okay, and to do that, we're going to get out our magic magnifying glass here and blow this up a little bit here. And you'll notice here that, okay, I'm showing you ds, I'm showing you the direction of the electric field, theta, the angle between, okay, r hat and ds. And you'll notice here that when we do the dot product here, okay, r hat dot ds, by the definition of a dot product, it's the magnitude of r times the magnitude of ds times the magnitude, or sorry, times the cosine of the theta, the angle between those two vectors. And remember, the magnitude of r hat of any unit vector is 1. ds is not a unit vector, but, okay, I want you to notice here that, okay, put in a magnitude of 1 for r hat. Take a look at how to interpret, okay, ds cos theta. Do you see here that when I'm looking at magnitude only, that ds times the cosine theta, we're going to call that dr. Okay, notice that, okay, ds cosine theta gives us the component of ds that is in, okay, the radial direction. So, and this is generally true here. So we can simplify this. The integrand here, E dot ds, we can write as kq over r squared times dr, because, okay, ds cos theta is the component of that displacement vector ds that is in the direction of r hat. And we'll finish this up on the next slide. So continuing where we left off on the previous slide here, okay, now that we know what that integrand looks like, we're in a position to calculate that electric potential difference, okay, which is just what we get by, okay, integrating that integrand and taking the opposite of it. Okay, this is just our definition of electric potential difference. So when we substitute in, okay, the expression that we just derived, kq over r squared dr, okay, and we now have to actually evaluate that integral. We'll do this in a couple steps here. So k, Coulomb's constant, and q, the source charge, or the point charge, those are constants that can be taken outside of the integral. Okay, we'll write the integral as r to the minus 2 dr. And when we evaluate this simple, okay, function here, then the integral of r to the minus 2 dr is just r to the minus 1 divided by negative 1. And therefore that gives us simply, okay, the negative sign cancels. We get kq over r evaluated from point A to point B. So here, doing this here, okay, point B is a distance r sub b from our source charge. So we really have, okay, we can factor out the kq and write this as 1 over r sub b minus 1 over r sub a. So as Bongo nicely tells us here, note that the potential difference between points A and B, okay, due to a point charge, depends only upon the radial coordinates, okay, r sub a and r sub b. That is it. Okay, so what we're ultimately interested in here is not the electric potential difference between 2 points in space, okay, but as we said, how about the electric potential at a single point in space? And remember what we talked about previously, that by arbitrarily defining the 0 point of electric potential, to be infinitely far away from the point charge, okay, we can now define the electric potential at a single point in space. So that's what we call V sub P. And we said that, okay, the electric potential of that single point in space is what we get by evaluating the electric potential difference, okay, when we start our problem infinitely far away, okay, at a position r equals infinity. So to calculate the potential at that single point P, let's take the potential difference between infinity and P, and you'll notice that, okay, our initial point being infinitely far away, when we substitute infinity in for r sub a, okay, 1 over infinity is 0. And now we come up with, okay, this very simple yet very important expression for the electric potential, okay, of a point charge at any given point in space. So this is how we can define our scalar field, okay, for a single point charge. Okay, notice it is simply given by, okay, Coulomb's constant, okay, times the charge itself, which can be positive or negative, divided by, okay, the separation distance between the field point and that source charge, point charge. Some things to note in our calculation of electric potential difference and the electric potential for a point charge. First of all, that integrand, when we evaluated, okay, E dot ds, okay, it was independent of the path taken between the points A and B. And remember, not to beat this point into the ground, but because the Coulomb force is a conservative force, that means the work done by that force, okay, and moving a charge between 2 points in space is going to be independent of the path taken. And remember that, electric potential energy and therefore electric potential are defined in terms of that work done. The electric potential difference, as we saw, depends only upon the distance, okay, of each of our field points A and B from the source charge Q. That was it. And we see here that the sign, when it comes to electric potential at a point, the sign of the electric potential would be the same as the sign of the charge itself. So looking at this definition here, we see that electric potential can be positive or negative, and since Coulomb's constant and distance are always positive, okay, it will match the sign of the charge itself. So we can say that, around a positive charge, all points around a positive charge, the electric potential would be positive, whereas for all points around a negative point charge, the electric potential would be negative. And finally, we saw that we defined the electric potential at a single point, okay, because we assumed that the 0 point for electric potential was infinitely far away. So that is our arbitrary choice of a 0 point, okay, but it is purely arbitrary and it must be understood, okay, in order to do this, in order to say that you can define the scalar field, okay, the scalar potential at every single point in space. To try to see what this looks like here, we're going to try to plot what the electric potential looks like. We're going to do a three-dimensional plot, okay, of V potential versus distance, and we will look at distance in the Cartesian plane. Okay, so we'll see what, okay, the potential would look like for, okay, 2 dimensions, both x and y. Starting with the case of a positive point charge. Well, just looking at the definition, you can easily see that, okay, as r goes to 0, that is, as the, okay, field point, as you get very, very close to the positive point charge, okay, we see here that the potential gets bigger and bigger. And at 0, it would go to positive infinity. What happens when you get very far away from the positive point charge? Well, as r gets very, very big, you see that the potential goes to 0. Okay, so if we were to plot this, like I said, okay, the vertical or z-axis being the electric potential, and you see here, two Cartesian coordinates, let's say x and y represented, okay, as well, you can see that we can kind of think of this, and this analogy is helpful, as a potential hill. And when we ask the question, how does a positive test charge move here? Okay, well, you can kind of think of it this way, that the positive test charge moves naturally away from the origin as if it is sliding downhill. Or said another way, if you have a positive point charge, then you know that a positive test charge is going to move naturally away from it. What about the case of a negative point charge? Well, in this case here, we see that as r goes to 0, as we get very, very close to the negative point charge, okay, then v gets very, very big, and it goes to a value of negative infinity. And similarly as for the positive point charge, as you get very, very far away, okay, from that negative point charge, okay, as r goes to infinity, okay, then the potential once again goes to 0. So if we were to graph this, okay, in a similar fashion, it's going to look like this. A nice analogy is we can think of this as a potential well or hole. And you can say that a positive test charge would move naturally towards the origin as if it were sliding into a hole. So in this simulation, we will see electric potential graphed in two-dimensional space. So really the electric potential will be represented as a third dimension for a two-dimensional Cartesian coordinate system. So what you see on your screen right now is really the two-dimensional Cartesian coordinate system. And right now there's no charge that exists in this two-dimensional space. So what we're going to take a look at in this simulation is really two things. First of all, how does the sign of the charge affect the electric potential? And secondly, how does the magnitude of the charge affect the electric potential? Let's start with the sign of the charge. So what we're going to do is we're going to add a charge, a positive charge of 1 nanocoulomb to this two-dimensional space. And as I said, we see here that, okay, it is graphed as the third dimension here. Okay, sorry, the electric potential is graphed as the third dimension. So we can really think of this electric potential as being a measure of elevation, or let's say height. And as we said, notice here that the electric potential is depends upon the sign of the charge. So for a positive charge, okay, we see that the electric potential at various points in space gives us what we would call a potential hill. Okay, let's now go ahead and change the sign of the charge from positive to negative. So we'll go from positive 1 nanocoulombs to negative 1 nanocoulombs, and let's see what effect that has, okay, on the electric potential. And now you can see that the electric potential is negative. Okay, and this is why we can think of the electric potential as representing a hole, okay, in this two-dimensional space. So the analogy of a hill for a positive charge and a hole for a negative charge, okay, when we're thinking about electric potential. So we've seen how the sign of the charge affects the electric potential, changing it from positive to negative, okay, that is the hill versus the hole. How does the magnitude of the charge affect the potential? Let's go again here back to looking at a positive charge here. Okay, and this is the smallest charge here of 1 nanocoulomb here. And I want you to take a look at what happens here as we gradually increase the charge from 1 nanocoulomb to its maximum value of 5 nanocoulombs. So here we have 1. Let's change it. Okay, let's double it here. Change it from 1 to 2. Okay, we'll now change it to 3 nanocoulombs, okay, to 4 nanocoulombs, and finally to 5 nanocoulombs. Hopefully you can see what effect that has on the electric potential. Remember that electric potential is linearly proportional to the charge. So as Q increases, as a charge increases, the electric potential doesn't fall off as quickly with distance. This causes the hill to widen, meaning that the slope of the hill actually decreases. Okay, in regions where the electric potential changes abruptly with position, okay, that would be a region where the electric field is strong. While in a region where the electric potential doesn't change as quickly with position, okay, as in this case here for the larger value of charge, the electric field is going to be smaller in that region. As we will see when we more formally talk about this concept, when we in our next lecture we talk about properties of equipotential surfaces, we will see that the electric field is really the gradient or the slope, of the electric potential versus position. Now that we know how to calculate the electric potential at a given point in space for a single point charge, we can now turn our attention to the problem of calculating the electric potential for a collection of point charges, what we call a discrete charge distribution. So let me start out by pointing out how our new approach, is different or contrasts the approach that we've been using so far. The previous method, what we've been doing up to this point, required us to know the form of the electric field. And if we knew the form of the electric field, then we can use the definition of electric potential difference, given we knew the form of the field, and we could then evaluate it. What we're now saying, however, is that if the electric field is unknown, or too complicated to integrate easily, we can use the principle of superposition in conjunction with the known electric potential of a point charge, to calculate the electric potential of a bunch of point charges. So, and as Bongo suggests here, this is really nice because the electric potential is a scalar quantity as opposed to a vector quantity. So that means there is no need to consider angles, vector components, or unit vectors like we've had to think about thus far using the definition of electric potential difference. So this method is much easier if you were able to use it. Now, according to the principle of superposition, if we talk about a collection of point charges, we can say that the total electric potential, let's say at the field point P, due to n point charges, and I'm showing you really, well, Q1, Q2, Q3, imagine you have any number you want all the way up to Q sub n. All we have to do then is take the sum of the electric potentials due to the individual charges. That's it. Calculating the electric potential of a single point charge is quite simple. You just do this for as many point charges as you have, and because we're talking about a scalar field, you simply add up the results. It couldn't be easier. So here, we can say that in shorthand notation, the electric potential at a given field point P is simply what you get by taking Coulomb's constant, multiplying by this ratio, let's say Q sub I over R sub I, as you let I, the number of your index number, be equal to the number of point charges that you have. So when we substitute this in, we can write it out long form as such. So it could not be simpler. All you're doing is calculating the electric potential for at a given point for each of the point charges individually, and you're just adding up the results. Remember, I keep pointing out here that Q, the charge, the point charge that you're looking at here, could be positive or negative, so you've got to put in the appropriate sign. So let's take a look at an example of using this approach for a discrete charge distribution. And as you can see here, we'll return to the example of the electric dipole, because it is a rather common and important charge configuration. So recall that the electric dipole consists of 2 point charges, plus Q and minus Q, separated by a distance of 2a. I'm going to show you, the position of each of these charges here. And you recall we found the electric field of a dipole previously, okay, but not at an arbitrary point in space. Okay, we found it right along the y-axis here. Now we're trying to be more general. We're saying let's find it at some arbitrary point in space. It could be anywhere. I'm showing you this point here, P. And we will say that R minus represents the distance between the negative charge and the field point, R plus the distance between the positive charge and the field point. All right. And we will say that this angle here, okay, is what we call theta. So we're first tasked with finding the electric potential at this point P, and again we assume this arbitrary 0 point that the electric potential infinitely far away from the point charge, okay, either of these point charges would be defined to be 0. That's where the 0 point is. So using our definition, we've got 2 point charges. We're just going to find the electric potential due to each of those charges at point P at our results. Okay, that's it. Okay, 2 charges gives us two potential terms here. Coulomb's constant times the charge plus Q over what I call R plus, okay, plus K times the charge negative Q divided by what I call R minus. And we can, and you'll see why we do this in part 2 of this problem, we can get a like denominator, a single denominator as follows. And you'll see that by doing so, we're able to make an approximation in the next part of the problem here. So without numbers, this is about as far as we can go here. Okay, and you see that, okay, it's very straightforward since the form of the electric potential of a point charge is very straightforward. So in the second part here, it says, consider the electrical effects of a dipole at distances large compared to the separation of its charges. So if we're talking about a molecule, for example, the distance between those atoms in a molecule is usually quite small in comparison to either the distance between 2 molecules, okay, or the distance between some instrument and a molecule, in which case this approximation is okay, very good. I say here many molecules can be modeled as electric dipoles. Okay, we can say that one side of the molecule acquires a slight positive charge. Okay, on the other side a slight negative charge. If okay, there is a if it is polarized, if there is okay, if it is a polar molecule, okay, the charges will not be symmetrically or evenly distributed throughout the molecule, in which case one side will okay, be more negative than the other side. So this is important in many in chemistry, okay, in many fields involving chemistry, okay, pharmacology, okay, the synthesis of drugs, et cetera, et cetera. You know, the physics of polar molecules is quite important, and what we're saying is that, okay, many molecules can be treated as a dipole even when it is not, the molecule does not consist of 2 equal and opposite charges. As long as you can get a charge separation, okay, from one side of the molecule to the other, which is quite common, you can treat that charge configuration as a dipole. So here in this part, we're asked to find the long-range potential of a dipole, okay, and come up with an expression for that. So what we're going to do here is we are going to, okay, take a look here, and we'll explain where this comes from here, the 2a cosine theta term. But notice here that, and you have to imagine that if P is very, very far away, if P is very, very large compared to A, then you would agree that, okay, R plus and R minus are going to be very close in value to one another. Okay, true R minus is always going to be a little bit bigger, but for very large distances, okay, we can say that distance is the difference in distance is insignificant. Okay, so for r much greater than a, okay, this product r plus times r minus, we're going to write as r squared. And let's take a look here. R would simply be, okay, this distance here. And so notice that r plus r minus, that's what we have in our denominator here. Okay, the expression r minus minus r plus, what we have in our numerator here, that's what I'm showing you is equal to 2a times the cosine of theta. So again, you have to imagine that r is very, very large compared to a, in which case, okay, this triangle I'm showing you right here would represent a right triangle. This would be a right angle here, okay, for very large distances. In fact, r minus and r plus would be nearly parallel when r is very, very big. So plugging that into the expression we derived in part 1, okay, we said r minus minus r plus, we said is 2a cosine theta, so we put the 2a cosine theta up there. Okay, r plus r minus, which we said is r squared, put that there. We can write the expression for the dipole potential, okay, at an arbitrary point P as follows. And I'm sure you've heard of this. Now you know where this comes from here. Okay, I'm going to write this expression here, okay, 2aq, we're going to combine that and we're going to call it P. That is what we call the electric dipole moment. We're going to return to this later here, this semester, okay, when we talk about okay, electrodynamics, and we'll talk about electric motors. We'll return to this, okay, but this is what we mean by the electric dipole moment here. And okay, finally here, just to point out here, remember that for while the electric field for a point charge, okay, goes as the drops as the square of distance, okay, gets weaker as a square of distance. Okay, notice here that the electric potential for a point charge, okay, gets weaker as distance to the first power, right, kq over r. Notice here for a dipole, however, the effect of having a point charge, okay, and placing an equal magnitude charge but opposite sign charge very near to it, okay, the effect of that very far away means that, okay, the dipole drops much more rapidly than the point charge. It drops as 1 over r squared, as you see here in this expression. Okay, and so hopefully you're kind of getting the hang of this by now. You saw the difference between the field of a point charge and the field of a dipole. Now you're seeing the difference between, okay, the electric potential of a point charge and the electric potential of the electric dipole. So what would happen if your charge distribution consists of so many point charges that you would consider the charge distribution to be continuous? Okay, continuous charge distribution. Well, we're going to still use this same approach. That is the principle of superposition. And just like we said for a point charge, okay, you find what the electric potential is at your field point P due to that point charge. Okay, and then you simply add up the contributions to the electric potential for all of your point charges. We're essentially going to do the same thing, okay, but we're going to break up our charge distribution into an infinite number of infinitesimal charge elements dq, where most often dq will resemble a point charge, and then we're going to find the differential, okay, potential contribution of each dq at the field point in question, and to sum it up in the language of calculus, we end up taking the integral. So this is an approach we see over and over. Let's start with our continuous charge distribution. We'll break it up into an infinite number of infinitesimal charge elements dq, where each dq will say is a distance r from the field point. And okay, usually when we break up our continuous charge distribution, usually we're going to consider dq to be a point charge. But for cases with the correct symmetry, Sometimes we can consider dq to be a small ring of charge or even a small disk of charge, okay, for certain special cases. Almost always, usually we'll consider it to be a point charge. And each charge element dq contributes to the total electric potential at the point P, okay, an amount, we'll say dV, okay, the infinitesimal potential contribution, where your expression here, okay, dV is equal to k dq over r. This is just the expression for a point charge. Simply replacing, okay, q for the point charge with dq and dV, okay, to represent that infinitesimal contribution of each dq. And as you know, okay, the challenge, as always, okay, when we actually want to sum up all of the contributions due to all the dq's, well, that amounts to taking the integral. We have to integrate over the entire charge distribution, and you know that dq and r must be expressed in terms of a single integration variable. Okay, that's the challenge. Remember that charge density becomes a link between, okay, charge and spatial coordinates. Okay, remember trigonometry, right? Triangle trigonometry can often be used to, okay, find relationships between your spatial coordinates themselves. The first example we'll take a look at is the electric potential due to a uniformly charged ring. So we know what the field of the uniformly charged ring looks like. We solved that problem previously, okay, when we calculate electric fields using Coulomb's law, okay, not Gauss's law. There's not sufficient symmetry to apply Gauss's law. Okay, but I think you'll see, like I keep saying, how much easier it is to calculate electric potential, okay, because it is a scalar quantity. So in this problem, we're told that a total charge, big Q, is distributed uniformly around a thin ring of radius A. What is the electric potential on the axis of the ring? Okay, this arbitrary point P I'm showing you in the figure. So as we said, we're going to break up the charge distribution into an infinite number of infinitesimal charge elements dq. In this case, where we let each dq represent a point charge. So I'm going to show you a couple of those dq's in the diagram here. And okay, you will notice that each of those dq's, it doesn't matter what, okay, dq I pick along that ring, any dq will be the same distance r, okay, from the field point P. So this is, not generally true, but it is true for this charge configuration. So here, as I say, each charge element dq acts as a point charge and contributes, okay, to the total potential at point P, an amount dV, that is the infinitesimal contribution to the total electric potential, where dV is equal to k dq over r. Okay, and as I've said, note that each dq is the same distance r, which from our figure is simply the square root of x squared plus a squared from point P. Notice that x and a are both constants, okay? They do not change. They are not variables. Okay, therefore we can write, okay, our expression for the infinitesimal, okay, contribution to the electric potential, okay, dV, as follows. Okay, all we're going to do is we're going to sum up all of our infinitesimal potential contributions by taking the integral. Okay, and when we do so, this is particularly easy because, like I said, notice that Coulomb's constant, okay, r, okay, the square root of x squared plus a squared is a constant, can be taken out of the integral. The only variable in the problem is really q. So when we sum up all of the dq's, all we get is the total charge, okay, big Q, in the problem. So we see that the electric potential, the total electric potential at the point P, okay, can be expressed as follows. And the approach here was really quite simple to apply. In this next and last example, we're asked to calculate the electric potential due to a finite line of charge. And as you see in the figure here, okay, we're told that the total charge of this line of charge, let's say a charged rod here, is big Q. The rod has a length L. we're asked to find the electric potential at a point P, which is located right along the y-axis, a distance a, okay, from the x or horizontal axis. So here, our approach, we're going to break up the charge distribution into an infinite number of infinitesimal charge elements dq. In this case, we'll let each dq represent that of a point charge. And given the total charge of the rod and the length, we can find the linear charge density lambda by taking the ratio, right? Q over L. So once again, link between charge and spatial coordinates here using this concept of charge density. So let's draw in each of these dqs. Okay, notice each dq is a distance x from the y-axis from the origin, and each dq has a thickness dx and is a distance r from the field point. We're going to calculate the infinitesimal contribution that each dq makes to the total electric potential, okay, by calculating this here, okay, dV being equal to k dq over r. We're treating each dq as a point charge. I say here, note that each dq is not a set distance r from point P, right? As we move along the rod, that distance r changes. So unlike the last problem, while r still does have a value of x squared plus a squared, you'll notice that x is no longer a constant as it was in the case of the charged ring. It's now a variable. So plugging in here, okay, we can plug in our value for r, which is a variable, x squared plus a squared. And when we use the concept of charge density, right, substituting in q over L dx for dq, we come up with this. Okay, we are now in a position to integrate using the principle of superposition, right? We're told that we can just sum up all the infinitesimal potential contributions, which amounts to taking the integral. To do that, you've got to get a single integration variable, which you will notice we have, right? X is the only integration variable once we use this concept of charge density to relate charge to X. And here, this integral, we can take out the constants. That integral is not a simple polynomial integral of the form u to the n du. So we can use a table of integrals to evaluate it. And when you do so, you find out that, okay, it can be expressed as a natural log of these two terms here. And okay, here when we substitute in our limits of integration here, okay, we're going to go from this end of the charge distribution, x equals 0, to the other end, x equals L. And when we do so, okay, we end up with, this expression here. Notice that we can leave it like this, or remember that when you're talking about logarithms, okay, the difference of logarithms is equal to the logarithm of the quotient. Okay, so we could, if we want, maybe combine those terms and write, okay, the difference of logs is a quotient of these two logs. Okay, so there you have it. There is, the evaluation of that integral is a little bit tricky, but the approach we're taking here is really straightforward, okay, really quite simple.